Welcome to our AI Factory full-stack troubleshooting overview. In this scenario, we will troubleshoot a slowdown in our containerized health application. This application is orchestrated by Kubernetes and backed by Linux hosts, each of which have multiple NVIDIA GPUs. Let's dig a little deeper into our health application to understand the relationships of the containers. Here, we are looking at a container topology automatically discovered by eBPF. We have a user interface that feeds an intake service, followed by a diagnosis service. The diagnosis service uses a replicated, locally hosted AI writer service which requires GPUs to create specialized medical documentation based on the doctor's findings. On completion, the file is sent to a billing application. An AI imaging service, capable of scanning medical images like X-rays and MRIs for anomalies, is also utilized. This service runs in batch mode due to longer processing times, and feeds both diagnosis write-ups and billing. With the application setup clear, we will now investigate the alerts dashboard for issues in the AIFO factory cluster. We immediately see two alerts indicating high response time for our AI writer service. Drilling in, we see response times hitting 16 seconds, well above the desired 5-second threshold. We also see some related alerts. We will come back to those in a minute. The Troubleshooting tab shows the slow Kubernetes service and the specific container experiencing the issue. The high latency path chart indicates unstable latency, alternating between acceptable and slow response levels. Returning to the related alerts, we see that an alert policy has identified some alerts from our infrastructure that might be related. Clicking on the related alert reveals its details. We can then drill down into the infrastructure for deeper performance analysis. Drilling down takes us directly to the I/O alert details. We can then examine the affected entity, a GPU in this case, to reveal the noisy neighbor process. This demonstrates how our alert policies automatically link alerts between two environments, and how that can help you quickly arrive at a root cause. Now, let's walk through the full stack to manually perform this same correlation. While checking additional key performance indicators, we'll return to the original slow writer alert detail. From the alert overview page, we can drill into the alert details and analyze and select the container in question. To find the root cause of this intermittent high latency, we'll investigate each layer: application, orchestration, and infrastructure. By selecting the container that is experiencing problems, we quickly see all of the relevant information required to troubleshoot this problem. First, we rule out application issues by reviewing container metrics like CPU and memory to check for coding problems, like a runaway process. In addition to container metrics, the logs from the containers and pods are scraped and associated with the relevant containers. These logs can be reviewed for help errors or exceptions. If application metrics and logs are cleaned, the next step is to review the Kubernetes events. We'll check for orchestration events like failures or pod issues by clicking the events link. We see no events have occurred in the last 24 hours. By expanding the time frame to the last 7 days, we can see if there are additional events during that period. In this case, there has been no activity since the pod was originally created. Having ruled out application and Kubernetes environmental issues, we'll now investigate the infrastructure layer. Clicking the Infrastructure tab directs us to the underlying GPU hosting the containers process. We track every process that the GPU is running and the related infrastructure on a per-minute basis. This lets us instantly identify resource contention by seeing what else is running on the GPU. The issue becomes clear. The writer instance gets only 2% utilization, while the GPU is at a consistent 100%. This noisy neighbor scenario is confirmed by seeing that the imaging AI service is consuming the remaining 98% of the GPU. The other writer instance, which is using its own GPU, is healthy at 10% utilization. We complete the troubleshooting lifecycle by returning to the original alert and triggering an automated remediation action using StackStorm, ServiceNow, or another integrated platform. Our troubleshooting workflow confirmed that noisy neighbor resource contention was the root cause of the AI writer service's intermittent high latency. Thank you for watching this overview of full-stack AI factory troubleshooting.